is let's look at all the things that we've been working with rational functions. We want to put it all together. First things first, factor the numerator and the denominator. Second part, remember that whatever's in the denominator is going to be excluded from our domain. So we said it says set equal to 0 and solve. I do set not equal to 0 and solve. And remember that domain and vertical asymptotes go hand in hand. So what I like to do next is I like to look at the vertical asymptotes. But we remember, the vertical asymptotes come from everything that's left in the denominator after canceling. Because if we go back over here to 3 says removable discontinuity. If we have something that can cancel, then we're going to have removable discontinuity. And then the root, or the x-intercept, we let y equal 0. The y-intercept, we let x equal 0. And then finally, we need to determine, do we have a horizontal or do we have an oblique? So let's look at example 3. I know there's other ones. Good practice for you. But let's look at example 3 for a couple of reasons. And maybe what you want to do is type it in first. I'm not sure. I'll type it in a couple of minutes. But really what it says on our front of our paper is that we want to factor first. Without spending all the time on factoring, we've got a GCF up here in the numerator. And we also have a GCF down here in the denominator. So we can't do any more factoring to the denominator, but we can factor some more in the numerator. And just make a note to yourself that you're going to split the middle. So this becomes x and x, 5 and 3 minus and plus. And x times x plus 4. And I'm going to pause the video for a second because I think I made a mistake. I did not make a mistake. So what we have here is we're going to start by finding the domain. And the domain is determined from the denominator. So we have x doesn't equal 0, which I can put over here on the blank. And we also have x minus 4 doesn't equal 0. So if we add 4 to both sides, we get x doesn't equal 4. That's our domain. But when we go back and look here, do we have anything that cancels out? It just so happens that we have an x in the top and we have an x in the bottom. Those are going to cancel out. And that part that cancels out is going to determine our removable discontinuity. The value that we got with that x value was 0, so our removable discontinuity is going to have an x value of 0. And the other thing that's going to happen is, because the x is canceled out, we're only going to have one vertical asymptote, and that's at the place where we didn't cancel out, the part of the denominator that didn't cancel out. And right about here, what we can do is we can look at our calculator, and I may have it typed in already. If we look at the picture, this one turns out a little bit nicer than some of the others on the picture. because it looks like we can see our removable discontinuity somewhere in here between 3 and 4 on the y-axis. There seems to be a gap right there. The other part here is that we just said that the vertical asymptote was x equals 4, which would be right in here. Does that make sense? Your calculator can help you determine if your answers are reasonable. So we've got the vertical asymptote. We can even put it in over here on our picture at 4. And let's find our removable discontinuity. The removable discontinuity, again, is coming from the value that canceled out. The x not equal to 0 in this case, then we change it to the 0. What we're left with is x minus 5 times x plus 3 divided by x minus 4. And we're going to put 0 back into every x there in that function. So it's going to be 0 minus 5 times 0 plus 3 divided by 0 minus 4. And we end up with 0 minus 5 is negative 5. 0 plus 3 is 3, and 0 minus 4 is negative 4. So it's negative 15 over negative 4. Negative divided by negative is positive. So our y value of our removable discontinuity is 15/4. By the way, if you prefer, that is 3 3/4. And once again, if we go back to the picture on our calculator, we even have a gap there. And that's also what we're going to draw our picture here, which is 0, 1, 2, 3, and 3/4. Somewhere right about there. We want to find the x-intercept and the y-intercept. Well, the x-intercept is determined by letting y equal 0. And the y-intercept is going to be determined by letting x equal 0. And once again, go back and look at your picture for a minute on your calculator. What happens with our graph when we cross the y-axis? It crosses here. What happens? There's an open circle right there. In this particular case, we don't have a y-intercept. Once again, notice where we put that open green circle. It's open. Open means not included. We don't have one. If you go to your calculator and you look at the table, at 0, what do you see? You see error. When x equals 0, we have an error. There's another hint that either there's a vertical asymptote there, or we have removable discontinuity there. But if you take a quick look at the picture again, can we identify x-intercept? And in this case, x-intercepts plural. And it looks like we've got one at 1, 2, 3, 4, 5, 0. And 1, 2, negative 3, 0. Let's go look at the table. Negative 3, 0. As we scroll through, 5, 0. Use the calculator to help you find those values. Again, we just came up with the fact that it's negative 3, 0. 5, 0. We didn't even really need to go to the table, but we can verify from the table. The concept is, do you know that y is 0 for an x-intercept? Now that we've done all that, the last parts are, do we have a horizontal asymptote, or do we have an oblique? And that goes back to our chart, which once again, if you haven't at least started to memorize, you should consider. But the degree on the top of this function is 3. The highest degree on the bottom of the function is 2. 3 is bigger than 2. This is a top-heavy function. And a top-heavy function means that we're going to have an oblique. And if we have an oblique, we're not going to have a horizontal. So no horizontal. So now we have to figure out what our oblique is. The thing about this is, remember, if we canceled out the x's, we can do our synthetic division, or if you prefer, long division, with this part that's remaining. The x squared minus 2x minus 15. And when we do the synthetic division, x squared has a 1 in front of it. Then it's minus 2x, so it's going to be minus 2. And then our constant is minus 15. We're dividing by x minus 4. So instead of putting negative 4 out there, we're going to put positive 4. If it was x plus 4, we put minus 4. But it's x minus 4, so we're going to put plus 4. And we're going to carry down the 1. 4 times 1. Positive 4 times positive 1 is positive 4. And negative 2 plus 4 is 2. 4 times 2 is 8. And negative 15 plus 8 is negative 7. Remember that that negative 7 is the remainder. That's the remainder. We don't need to worry about that. We started with x squared. When we divide, we decrease by a degree. So this leaves us with 1x plus 2. You don't need to write the 1, because an oblique asymptote is in slope-intercept form. So we've got y equals x plus 2. When we graph that, the slope is 1 over 1. Y-intercept is 2. So here's b equals 2. And it's up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. We can go down 1 to the left. And I usually just put a whole bunch in there, but we can dot that up. And one last time. We know what the x-intercept and the x-intercepts are, sorry. Negative 3, 0. And 1, 2, 3, 4, 5, 0. And we can get our picture. Here. And here.